Oh, it's okay. All right. So how you guys doing today? Good. You guys have a lot of finals. Yeah. Okay. So, but the good thing is what our final exam will be Canvas online, right? So make sure you guys go find the syllabus on the modulus menu on Canvas. It says the date and time, and also I'm also gonna maybe post some Canvas announcement so you can how you can take the final exam on Canvas, but it will be literally the same as you did for Canvas quiz. Okay, so if you just click the quiz tab menu, and it says that instead of the quiz number or something, it'll be final exam on certain day. Okay, so that's okay. All right, so we've been doing the review session for final exam. So final exam will be comprehensive. So it covers all the chapters, but the good thing is what? It's open book test. So you don't really have to memorize them all, but you only need to know how to solve the problem. So let's try the problem here. Okay. So maybe if you have this one. So you have a 0.025 moles of this butane, okay? And then try to find out the numbers of hydrogen atoms. That's the question. Okay? So you have a chemical formula for the compound, the molecule. This is about 0.025 moles, and then we can just try to find out the numbers of hydrogen atoms. So the 1 mole is equal to 6.022 times 10 to the 23rd. Okay. This how many 1 mole is. Okay. That's what the number is. Okay. So maybe 2 minutes, I think. We can try it first. So we can do this together. Okay, maybe 1 minute. Okay, so this is the formula, and then we have this many moles of the butane, okay? And we try to find the numbers of hydrogen atoms, and 1 mole is Avogadro. Okay, so yeah, let's do this together. So we know we have this many moles of molecule, but to get the numbers of hydrogen atoms, you just need to count the numbers of hydrogen in the compound. So that is about 8 hydrogens in 1 compound, right? 8 hydrogens in 1 compound. Okay. So for example, if you have 2 compounds, that means actually they're going to be 16 hydrogens. Because it's 2 times 8. Okay. So to get the numbers of hydrogen in moles, you just need to multiply this number by what? 8. Okay. Makes sense, right? Because you have 8 hydrogen for each compound. So if you have a numbers of a compound, just multiply that number by 8. Okay. So if you do 0.025 times 8, it will be 0.2 moles. Okay. So you have a 0.2 moles of what? The hydrogen atoms. Okay? But the thing is 1 mole is equal to Avogadro number. So you can just simply multiply this number by Avogadro number. Okay? And then you see the moles cancel. And then you can actually get the actual numbers of hydrogen atoms, which will be what? Okay. Makes sense, right? Yeah. Okay. So that's the Can you guys get the number for carbon instead then? Carbon. Carbon. Okay, about 1 minute. It's pretty much the same, just different number for carbons in each molecule, and that's it. Okay, so yeah, so instead of the hydrogen, we have carbons. So you have 4 carbons. In each compound. So we're gonna multiply this number by 4 at this time because it's 4 carbons in one compound. So this will be what? 0.1 mole. Okay. And then we're gonna multiply that by Avogadro number, 0.1 mole. So you're gonna get 6.022 times 10 to 22nd carbons. Carbon atoms. Okay. Okay. Makes sense, right? I think I can move on, right? I can move on. Yeah. Okay. So let's move on. Okay, this is also what we did before. You can try to count the combustion reaction. And we say we have maybe 66 grams of propane, and we said we have 300 grams of oxygen. Okay, and try to guess how many grams for each. Okay. This will take quite a time, so I'll give you 5 minutes. The first thing you need to do is balance the equation first and try to find out the molar ratio between these two reactants and see which one is going to be your limiting reagent. So once you choose your limiting reagent, stick to that moles number to get moles of these two. And then once you get the moles of the product, multiply them by its formula weight, molecular weight. Okay, maybe 4 minutes. Okay, about 2 or 3 minutes. Yeah, this will take some time, but start with the balanced liquid. Okay, about 1 or 2 minutes. Okay, so yeah, let's do this together, okay? So if you look at this one over here, you need to get the molecular weight first to get to know how many moles of each you have for reactants. So if you look at this one, carbon is 12 grams per mole. It's the atomic mass, okay? And then hydrogen is 1. It's 1.0 something, but you know, it's 1, okay? Approximately. So you have 3 carbons, okay? You have 8. So this will be 36 plus 8, so it will be 44. So this means if you have a 1 mole of propane, that will weigh about 44 grams. That's what it means. So you have actual mass, you have 66 grams of propane. But if you try to divide this number by molecular weight, which is 44 grams per mole. Okay? So if you look at this one over here, the unit for the mass will be canceled, and then you get a numbers in moles. Okay? Because moles is the denominator of denominator. So approximately, you're gonna get about 1.5 moles of propane when you have 66 grams of it. Okay? So that's what it means. So we'll do the same thing over this oxygen here. Make sure your oxygen is diatomic molecule because it's unstable as mono. So they had 2 oxygen there. So each oxygen weighs about 16 grams per mole. Okay? So that's why you actually got double this number to get the molecular weight of the gas, oxygen gas molecule, 32 grams per mole. Okay? So we'll do the same. We know we have 300 grams of oxygen. So try to divide this extra mass by molecular weight of oxygen gas molecule. So we'll get you a number of 9.375 moles of O2. So you have this many moles of O2 here. And then you have a moles of the propane, oxygen gas molecule, both of them. And we're gonna use the stoichiometry to find out which one will be our limiting agent. So we have maybe 1 here that makes the 3 and 4 water, because if you look at this one, just 1 molecule makes 3 carbons and 8 hydrogen. To make the even number for the other side on carbons and hydrogen, it has to be 3 carbon dioxide at least and 4 water, so making 8 hydrogen. That's the minimum you can try. And then this will make 3 times 2, 6, 4 times 1 is 4. So in total, you have 10 oxygen on the right side. So this is diatomic molecule, so I'm gonna put 5, that makes 10 oxygen on the left side as well. So this is balanced now. So that means actually, if you have a 1 organic compound, you need to have 5 oxygen gas molecule. So if you have a 1.5 moles of propane, you should have 5 times bigger numbers of oxygen is needed for them. Okay, so 1.5. So I'm just gonna compare this one to tier. So it'll be 1 to 5. So it'll be 1 over 5. This is the amount of the oxygen you need to have for 1.5 moles of the propane. This is about 7.5, right? 7.5. Okay. So this you need to have a 7.5 moles of oxygen is required for 2.5 moles of propane. But how many moles of oxygen you have actually? It's 9.375. So you have more than what you need for that propane. So which one is the limiting reagent then? You have more than what you need for oxygen, but you have just 1.5 moles of propane. So it will be propane or oxygen? Can you guys guess? Propane, perfect, yes. So in that case, you don't have to worry about this one anymore, because this will not be 100% used. There will be still remaining numbers of moles of oxygen gas molecule, but this one will be all used up if there's 100% reaction there. So we're gonna stick to this one, and we're gonna compare the molar ratio from to the reactants to product. If you look at this one over here, propane, 1 propane goes in, it makes not just 1, but 3 and 4 carbon dioxide and water. So if there's 1 mole is used up, you're going to have 3 moles of carbon dioxide and 4 moles of water will be formed after reaction. Okay, so 1, 2, 3, 1, 2, 4. So you have 1.5 moles of propane goes in. For carbon dioxide is 3 over 1, which is 3 over 1. For water will be 4 over 1. Okay. So for this one, you're going to have what? 4.5 moles of carbon dioxide will be formed. Okay. And then you're going to have 6 moles water will be formed. Okay, and the rest is pretty much same, simple. You just need to multiply this number by its molecular weight, 44 grams per mole. Okay, so carbon is 12, 16. 16 times 32 plus 12 is 44. So if you just do that, okay, you can get the number for numbers in mass, okay, for carbon dioxide. Same thing here, 6 times 18, okay, that is the grams of H2O. That's pretty much. It'll be 105. This is about something. Yeah. So you can do it in the calculator. You can get the numbers in grams now. So whenever you have 30 grams of these two reactants, you can just try to start with the balance in the equation and find out the molar ratio between the reactants and see what will be your limiting range, and then stick to that moles number to get the moles of products by using stoichiometry. So 1 goes in, 3 and 4. So that number of moles will be produced by as the molecular weight. You can get an actual amount of the mass of each product will be. Okay. Makes sense, right? Okay. Okay. So, okay, let's do another. Okay, so let's try. I think this is quite the. Okay. If you have this one here, what might be the net ion equation for this one? Maybe 1 minute. You can try. 1 minute. We'll do this together. You have. What's the name of this one? Can you guys try this one? HCl. It's a binary acid. How do you name it? Be hydrochloric acid. Yeah, perfect. Great. So we have a hydrochloric acid and sodium hydroxide. What might be the ionic equation? Net ionic equation for this one. Okay, about 30 seconds. We'll just. Okay, so here's the thing. So whenever you have you're going to take the final exam, one thing you can keep in your mind is that everything that I'm going to put on the final exam will be strong acid and strong base. So I'm not going to put any weak acid and weak base on the final exam because they will be covering Gen Chem 2. So this is a strong acid and this is strong base. Okay. So why am I emphasizing their strong base and acid is because they will be fully dissociated in water. If it's weak acid and weak base, they will not fully dissociate. So that all not counted as the stoichiometric wise not correct. But anyway, because luckily we have a strong base and strong acid and strong base over here, meaning they're going to all ionize. Everything, most of those two will be ionized in form of cation and anion. Okay, so if you look at this one over here, you can have these two from here and here. Okay? So if you try to recall what we learned about the definition of acid and base, the acid is defined as what? Donating hydrogen cation. Or you can say donating what? Proton. Because if you think about the hydrogen, it's simply just one proton and one electron. If you look at the periodic table, it's atomic number 1, that is proton. That's one proton. It's just paired with one electron is neutral, but when you lose electron is cation, just same as proton. So either way, if it donates the proton or a hydrogen cation, that is become our acid here. Okay, and this is also donating OH minus. So following the Arrhenius definition of the base, that is our strong base. So whenever you look at the strong acid, strong base mixed together, they're going to do neutralization. Neutralization. Meaning they're going to neutral together because these two, hydrogen cation plus OH minus, will form water. water is pH level wise in neutral form. Okay, so this is the aqueous form. This is an ion, and they become water. Okay, so we'll be neutralizing them to each other. So it's very acidic, very basic, become neutral together by becoming water. Water is obviously a pH level. You guys actually will learn why water pH level is 7. It's because of the autoionization that you learn in second 2. But for now, only thing I want you to remember for the exam is that whenever you have a strong acid and strong base, the net ion equation will be always this one. It doesn't matter if you mix with like maybe some hydrochloric acid with the potassium hydroxide, or some of the strong base will still be. This is our net ion equation for neutralization. So hydrogen cation plus OH minus will become water. Later you're gonna learn about the Lewis-Bronsted-Lowry definition. You're gonna learn about the hydrogen cation and some of the Lewis acid base. But for the final exam, this might be just good. Okay. Does it make sense? Good. Perfect. All right, that's good. So so maybe one more thing. So try to get the pH. Try to remember this one. pH is a negative log of concentration of hydrogen cation. Okay, just remember this one. Okay. So for example, you have a 0.001. Okay, 0.001 molari HCl. Okay, you can assume there will be same concentration of hydrogen cation solution. Okay, so only thing you have to do is put this one in negative log. Okay, in your calculator. Okay, so then there will be pH level 1, 2, 3. Okay, so that's it. Okay, it's pretty easy, right? Negative log, and put the concentration of your hydrogen cation, which should be same as your strong acid concentration. This will be just 1-to-1 ratio. Okay, makes sense, right? Okay, so last time I think if you remember, one of the question on exam 2 was this one: if it's true or false. That's absolutely false because it's a negative sign. Okay, so that's why it's when negative it still becomes 3 positive. Okay. All right, move on. Okay, so let's try to do, if you have 8 grams of iron 3 sulfate, okay, and in final volume of 250 milliliter. Okay, what's the concentration? So concentration means always in chemistry moles per liter. So I'll give you 4 minutes. This is a quite long too. Yeah. So for those one, you need to look at the atomic numbers on the periodic table and just multiply them all to get the formula weight. Okay. So then you have actual mass of that, and then you can divide that actual mass by your formula weight, and that will get you the numbers of moles. And then you can try to divide that by this one, but in liter. So you have to do the unit conversion. Yeah, if you look at the periodic table, if you don't see it, I'll read it for you. So iron is 55.845. Sulfur is 32. Oxygen is okay, maybe 1 minute we'll do this. Maybe 1 or 2 minutes we'll do this together. Okay, so yeah, look at this one over here. So we have a 2 ion, right? Okay, and then you have 3 sulfur, okay, 32, and you have 12 oxygen over there. Okay, so if you do that all, you'll get the formula weight is equal to 399.88 gram per mole. Okay. So if you do the 8.0 grams divided by formula weight, 399.88 grams per mole. Okay, and then you'll get about 0.0200 something moles. Okay. Okay, and then you just need to divide this one by formula weight. I'm sorry, final volume. But to get the concentration, you need to have moles per liter, right? So, but this is a milliliter, so you have to convert that into liter, which is the 1,000 milliliter over 1 liter. Okay, so the milli means a 1,000th of something. So that's why 1,000 milliliters equal to 1 liter. So if you do that, you can divide this one by 0.25 liter. So you have a concentration, molarity concentration unit right there. Okay. All right, so that will make approximately what? The 0.08 molarity. So yeah. Can you guys double check this one? I think I'm right, but yeah, it should be right. It's like a 0.020006 something, but I will just ignore them because I don't think it's very yeah. Okay. Makes sense, right? You good? Okay. All right. Let's move on. Oh, is it the oh the one? Okay. Alrighty. Maybe you can try. You have 0.250 molar concentrate HCl solution. So this is your stock solution, and you want to make 500 mils of 0.0125 molar concentrate HCl. Okay. So how many milliliters of 0.25 molar concentrate HCl is needed? That's the question. So you're gonna do dilution, putting a lot of water or on certain volume of the stock solution. So you kind of make dilution by mixing that with water. But how much you need to have that make this solution? So this is the stock solution. We normally call this is a working solution because this is a solution you're gonna work with something. But yeah. So this is what we learned from this one. Okay, try to use this one. Okay, about 3 minutes. Okay. Okay, well, about 1 minute. Okay, so it doesn't matter which one goes which. Just you make sure you put it on the right ones on the same side and the other side. So I'm gonna put this in here and here. So I'm gonna put the this M stands for molarity, it's concentration. This is the volume, and this is the other dilution form. So maybe you can do 0.250 molar times X milliliter, because that's what we're solving for, okay? And we know what the working solution condition. We have a 500, let's do this one first, 1.0125 molar concentration, and we want to make 500 mils of it, okay? So if you just do this one, it's pretty simple now. You only need to do what? This one, okay? So once it was multiplied, but on the other side will be divided, right? Okay, so you just need to put this one. Okay, so units to cancel, you get the numbers in liter, which is your X, which is what you're solving for, okay? So if you do that all, you're gonna have what? This will be what? 6.25 divided by 0.25 will be 25, right? Could you guys double check this one actually? Yeah. Could you put this in calculator? 0.0125 times 500 over 0.25, okay? It will be 25, I think. Is that right? You guys not doing this?
I got
250? Let me try. Let me try that.
I got 25.
You have 10. Okay. I think it's 25. Let me double check. Go. 1.1. I think it's the 25. Yeah, it's 25. Okay. So I think you're missing 1 0 here. Okay. So it's 25. So that means what? You have a 25 mils of stock solution, which is this one, and put it in the beaker. So you have a 25 mils of 0.25 molar concentrate, and we're gonna put the rest to get 500 with water. Okay, so meaning what? 475. Okay, so it's 500 minus 25 is 475. So we're gonna add a 475 mils of water into there with the 25 mils of the 0.25 stock solution. So it become diluted, but solution for your working solution. So it's done. Okay. Okay. Do you want to do one more? Can I move on? Okay, I can move on, right? Okay. Perfect. All right, so let's do some oxidation number, okay? So whenever you have some polyatomic ions, looks like this, what might be the oxidation number for phosphorus, okay? I'll give you about 1 minute. Okay, meanwhile, can you guys try this one too? What might be the oxidation number for nitrogen? So we're looking for oxidation number in the polyatomic anions. So the key point here is that you can memorize that the oxidation number of oxygen is -2. And then your formal charge will be the same as the sum of the oxidation numbers in the elements of the compound. Okay? So if it's neutral, sum of the oxidation number has to be 0. But in here, sum of the oxidation number should be -3, -1 in sum for each. Okay? So that will tell you some number. Okay? Okay, so how about this one? What number? +5. Perfect. All right, great. See, this is -2. There's a 4, so it's -8. But with that, oxidation number has to be -3, so it has to be 5. Okay. How about this one? It's also 5. It's perfect. Because you have a -2 but 3. So it's a -6 now. But with that addition of the oxidation number nitrogen has to be -1. So it's a 5. You get it, right? Okay. So only time you're gonna have a different number for oxygen, for oxidation number, it will be hydrogen peroxide, but I'm not gonna do it on this. So most of the time, the oxidation number for oxygen will be -1. And then, okay. So yeah, this is the last one today. So if you have a system, you have a surrounding, okay, and then your system gains 170 joule amount of heat energy, okay, and then system did a work of 210 joule. Okay. So what might be the energy change of system? That's the question. So what's the change in energy of the system? If the system gains the heat energy from outside, it was about plus 170 joule amount of heat energy. And it also did a certain amount of work. It was about 210 joule amount of energy. Okay. So what might be the change in energy of the system? Okay. About just. Oh, you guys already did, right? Okay, good. So the system gains the heat energy. So this will be obviously 1. This will be obviously 1. Obviously 1 plus, right? Because it gained the heat energy, right? How about the work? The system will be perfect minus, because the system did a work for something else. So to do the work, system has to use the energy, meaning they lost that amount of energy to do the work. So it's to be -210. So in total will be -40. Perfect. So the change in energy of the system was actually negative, because they got certain amount of heat energy, but they used more energy than they got from the heat for work to do. Okay, so it's in total actually slightly negative for the system. Makes sense, right? Okay. All right, so that's it for today. Let's do extra credit.